Thank you very much for organizer for bringing me here. And also thank you for putting me in experimental session. I lately become involved in some experiment, but it's the first time that I present two experiments. And I do have some connection, although they are not done in Tel Aviv, but I was involved in one maybe more and another one maybe a little less. But again, I think my part is more about interpretation, and I will not talk too much about experimental details. I was trying to think what I can say about David Bohm, and this experiment I don't think they're related to Bohmian theory, but during this talk I have some remarks, but maybe I can say it. I was privileged to meet David Bohm a few times, and especially I remember a full day in South Carolina. I took him for sightseeing in Charleston, and I had a full day discussion of physics. And I know Bohmians. I know many Bohmians. I had many talks about Bohmians, and we had some talks here. And I think David Bohm will disagree. For me, Bohm is number 2. I think I'm very sympathetic to Bohm. And for me, it's a candidate for final theory. And for many Bohmians, this is the theory. It's a kind of historical mistake that people that teach standard quantum mechanics, it's not Bohmian mechanics. And when I talk, David, I like your theory. This is deterministic, and it's not. And this is what I would like to see of the final theory. Nonsense. There will never be final theory. I invented it as a next step. This will help us to develop more theories. So then I was happy that Bohmians here kind of was against hard-nosed Bohmians. The generalization of Bohmian was stochastic. They would kind of never accept it. But this is a way to something new. So definitely, Bohmian theory brings us new physics. Happy birthday, David. Okay, I will talk about 2 experiments. The first experiment was done in Italy, and in fact, they didn't let me touch almost anything, but we discussed what they're supposed to do. And Eli Cohen, in fact, brought me to this collaboration, and I think maybe natural that I was there, because this is the first experiment of protective measurement, the work which was done with Yakira Aronov a long time ago. And now, maybe the question, let me come back to the title of my talk was, are expectation values and weak values are properties of a single quantum system? So this first experiment was really done with single photons. So this kind of should tell us. It's a good experiment. It should tell us about this. However, I don't think that the conclusion of the experiment is too strong to say that expectation value is a property of a single system. It's supported in some way, but even I have serious reservation. Second experiment was done in Munich, and from Israel is Alon Ben Israel, and I think Jan here from people who took very serious part in it. Here I think I was more in the laboratory, also again, I almost didn't touch anything there. And this experiment was not done with single photons. This was an experiment with a continuous light, but I believe that it does teach us that supports the idea that at least weak value is a property of a single quantum system. I don't need any kind of support. I believe that everything is a wave function, and everything, we don't need any ensemble. But this is my interpretation stuff, and here I talk about experiment. I think still, this experiment, even for people who look just in operational meaning, supports the idea that it's property of single system. Okay, let's start with first expectation value, and I think there is still looks somewhat amazing because we measure expectation value, a statistical property, using a single photon. Really, we had a single photon source and a single photon detector. Single event told us something about something which conceptually is statistical. Expectation value of polarization operator. We had some single photon in particular polarization state. Its expectation value was some number, 0.2. And we had this kind of new model, advanced single photon avalanche diode array. Everything, it's a single photon detector. And also, it's always heralded single photon source. And we started, and some clicks start appearing. In fact, there are many thousands, but we also did some runs with few. And this is kind of an experiment of polarization, because we had some bidiphrygian crystal. We're supposed to push to the right or to the left, depending on if it's H or V. And what? How? The whole detector, again, the details, I'm not, the whole detector, it's, the whole detector, it's something like centimeter, it's letter list. It was 32 by 32, and we didn't use part of it. 32 pixels. So you see, we can see that we get more clicks here than clicks here, and we can say that the number defined, but we had 5 around +1, which was H, and 9 about V. So we could calculate expectation value, and the number was 0.929 minus 0.29. This is minus 0.2, something reasonable. Anyway, this kind of experiment expectation value, we can have eigenvalues of polarization operator, which might be only 1 and -1. So, of course, expectation value found in statistical way. Some randomness. So, but then we repeated it, and we repeated it with protection. Now, it was essentially the same system, and we added protection. We added protection, and we sent a single photon, and we got 1 click. And this 1 click gave us also a reasonable number. It gave us, you see, every time, depending on this, this is correspond to -1, this is to +1. So what here, it's minus 0.3. A single click which gives us expectation value. Now, the work was about protective measurement was like 20, 30 years ago, and people discuss the meaning, and also we'll discuss a little later. But the experiment, as far as I understand, only this is the first experiment. This is kind of real experimental data. This is in the end what is kind of amazing. A single click gives us a number. But to be sure that this single click gives us a number, we had to test our system. So we put thousands of photons, and this is what we got, the statistic we got. Without protection, it was around 1 and -1, this one. And when we add the protection, we got a single peak. Now, even when we get a single click, we can believe, because this is our system, we tested it, that this tells us about expectation value of our single photon. Schematically, this is what happened in our experiment. During the experiment, H and V would start separated, and then they came here. It was kind of had some uncertainty, and we get this click. Now, in the protective measurement, we added, in addition, a xeno-type protection. During the process, we tested every time that the state didn't change. We made projection measurement on polarization state of the photon during the experiment. And then The wave packet didn't split. It didn't split, but it did shift it according to the expectation value of the polarization. Maybe a little more. This was kind of a system. We had, in fact, it was not one piece, but conceptually considered one piece. And in this one piece, by diffusion crystal, H and V go separate during the process. But when we added the projection, the xenotype projection, these were kind of polarizers. We had 7, in fact, polarizers which arranged the projection. So we started with our state, but then every time we didn't let the state be spoiled because we didn't let it to be really entangled. And we added polarization filters. In the end, we got this one click. And this one click in the place, and the place gave us the number of expectation value of polarization operator. Let me be maybe a critic. I claim that we measured expectation value of this photon which started from here. But in our measuring device, we had these 7 filters with exactly the same information because it's only photons with this, then they pass through. So one way to say there is Alice who makes the experiment. She made this bi-diffusion crystal, and she really makes. And there is Bob who put the filters. Alice doesn't know what Bob puts. So for Alice has only coupling to the photon, and she finds the expectation value of polarization operator. And Bob is responsible for protection. So he knows. One can say we cannot do it for this experiment, but in general, for protective measurement, Bob does not have to know exactly the state he wants to protect. If a Hilbert space is bigger, only what he has to know is which possible state he wants to protect. It might be it should be eigenstate of the observable it's measured. Here we have only dichotomic variable, so there is no something of interest. But in principle, what have to be done in all this protection is just to test that this is one of the eigenvalues. So Bob might not know the wave function, of course, and if he doesn't know exactly the eigenstate, he doesn't know the expectation value of protection. So I would say that this experiment does show that property of a single particle. The experiment was done with a single particle, but single protected particle. If it's not protected, it's impossible. No cloning theorem tells us we cannot find expectation value of unknown quantum of some variable when its state is unknown. So there is some support, which I don't need, that everything quantum mechanics describe single system and not ensemble. But it's not a decisive experiment in this kind, on this type. Anyway, first time that it has been done. To talk about second experiment, I have to introduce weak values. And they already, Ephraim gave a very good introduction, but I want to add something. First, just state again. The two-state vector formalism tell us that when we make quantum measurements, there is a wave function going forward in time and also backward in time. So if we later make another measurement, in between the system described by 2 quantum states. One going forward in time and one going backward in time. And the complete description in this interval is really this two-state vector, which has 2 states. Now, the interesting part, one can find kind of paradoxes, 3-box paradox. We don't need weak measurement, but if we add weak measurement, there is really interesting stuff. If in between we make any kind of weak coupling, any kind of weak measurement, any weak coupling will be a coupling to this particular simple expression, the weak value. Now, this is how it's usually presented. This is how we presented it 30 years ago. But I think sometimes there is misunderstanding. And I want to put an accent on the fact that the weak value is a property in a particular time. It's not a property in this period. It's not a property of pre-selection, post-selection. We need to know what quantum state here going up and what quantum state going backward in time here. This is the meaning of two-state vector. It's not for the period of time. It's just for every moment of time. In the original experiment, the coupling was weak. It didn't change the state. So we had the same description here, here, and here, and here. So we didn't have to emphasize that it's particular time because it was the same everywhere. But it's really important that it's in particular moment of time. And the same, the concept of weak value is in particular moment of time. At every moment of time there is weak value. If the coupling is weak, it's the same. But in principle, it might be not. So this is why I was trying to defend it without success when people were telling that we can strongly measure weak values. There's no such thing. Because strong measurement changed the system, and the weak value, if we put the strong interaction here, the weak values will be different. Okay, so we have to look in particular moment of time. But now I really want to come to strong. The concept weak value, weak measurement. I think that it's really related, it's more basic. I believe at every moment of time there is a weak value, and this weak value is a weak, maybe good for this weak measurement, but it's not weak. What I mean, every coupling of a system in particular time, when the system is pre and post selected, is to the weak value. It shouldn't be weak. What it needs to be, it should be short. Of course, if I want to consider a moment of time, of course it's short. And it may be very, very short. When it's very short, then it's weak value. And I have to, at every moment of time, it's a robust property of a pre and post selected system at a moment of time for any coupling. When the time is small enough, then the effective coupling is to this weak value, which comes from the weak measurement concept, which came from the measurement. So we have to look exactly in a particular moment of time which wave function arrived from the past, which wave function arrived from the from the future. And now any interaction, not necessarily weak, its interaction with a variable c will have to is described by this. If we have coupling to c, then this is what will describe our interaction. How I know it? Chi is my external system, the wave function. If I want to know how it will change due to infinitesimal time, and I say that the weak value will tell us how it will change. I start with chi time the initial state psi. I made this coupling, revolution during small time, make projection, and then after a very simple calculation, what I will get, that I can write down the wave function of my external system due to infinitesimal time interaction according to this simple formula. It really, I have to replace in my Hamiltonian my operator c by c number, the weak value. This is the same if, like the case when the c is an eigenstate. If my state has an eigenstate of c, then of course the evolution is exactly this, even for when dt need not to be infinitesimally small. Here I said it's always because still there are some correction if dt is final. The question which we asked in this experiment is this equality is more close than maybe possible this equality. Because sometimes if I start with system which has expectation value, and I do it in infinitesimal time, very tiny. So maybe during this tiny time, I really have a coupling to expectation value. I consider cases when numerically eigenvalue, weak value, and expectation value, they all the same. And I ask how my external system will behave, will react on the coupling during to infinitesimal time. So this is the state after the coupling in weak case, in this eigenstate, and I have to write a density matrix in case of expectation value because I don't have a pure state. If I couple my external system and I don't make post-selection on the system, then I have some mixed state of my external system. But still, mixed state sometimes I can compare a mixed state close to another state or not. The way to compare when I work with not just states but also mixed state, I find the Burus angle, which distance, it's you can use fidelity or anything else. I like this one. And with help of people in Germany, we make this calculation, the general calculation, and we calculated that the general result, that the distance between the state of eigenstate and the weak value, when they equal, it's the distance between the final states which we get, it's really very small. Why it's very small? Because it's proportional to this small parameter square. And if it's expectation value, then it's first order, much bigger. And the first order is really not acceptable. Because, of course, the distance is small. When I make coupling for infinitesimal time, I'm even very close to the original state. I cannot move to orthogonal state very fast. For very small time, I'm still very close to original state. So if I just look on eigenstate and look how much it changed due to the infinitesimal time, I get something very similar to that case. But this is from the distance from the original state. And this is a final state in all these two cases, when they are all equal. We would suppose to believe that they all these three supposed to be more or less the same, and the expectation values are different. And what we did this experiment, it was not simple. Why? Because all this is very small. There are small differences. We are looking on, again, not infinitesimally small, but small coupling. Maybe why it's somewhat surprising to get this result. I consider this hypothetical example not what we really measured. I consider the case of, here we have some charged particle, and we look on the electric field here. When the particle sits here, there is a well-defined electric field here. So there is it's eigenstate of an electric field. I call it 1. The value of the electric field here is 1. And I look what's happening to some measuring device which make coupling to it. During infinitesimal time, this infinitesimal time not so infinitesimal, you saw the motion, you see? This is my infinitesimal time. It shifts in particular way. Now, this is a new state after the coupling. I consider a somewhat similar case, expectation value equal to the same number 1. How I do it? I put superposition of charge a little closer, a little far away. This one will be 0.5. Field, and here the field is bigger, 1.5 equal. So the average still 1. We have coupling. We have two states. One moves 0.5, 1, 1. Average, it's the same average. If we look on this, it's really a density matrix, but more or less it's the same story, very close. Now I consider weak value, which weak value, you know, there might be anomalous. So they may be strange. I consider a situation where my eigenstate are really very different. My charge is really in superposition of sitting here and here, pre-selected and post-selected. So it's supposed to give the field to the left. But because of the particular post-selection, the weak value is really the same, still 1. The picture, what's happening during the process, we have motion to the left, motion, another motion to the left, everything moved to the left. But after the post-selection, we get something again very close to the original one. And the claim is that this and this much closer than this one to this. Experiment. Now, before the experiment, really, we wanted to make experiment. We couldn't make experiment which I presented. And we more or less what we did experiment with spin 1. Even this not exactly, but let's explain first spin 1. And the simple case, we have, I said I make expectation value, eigenvalue, weak value, all the same. Here it was something very trivial, 0, all 0. So I have spin 1 particle, and my eigenstate is spin 0. My expectation value made out of other eigenstates, -1 and +1, equal weight, so it's again 0. My weak value, pretty boring, but still supposed to be different. I start with the same state, and I post-select the same state. In fact, beginning, we thought that it's the same story, because weak value equal to expectation value. But I say it's a very different story when you print post-select. When you print post-select, your system you coupled with will be in a pure state, and it will behave differently. The number here is the same. So this is kind of experiment we wanted to do. But again, spin 1, it's difficult. What we do is the same polarization we did we did it finally in polarization. And what we wanted to do is to compare the results. Eigenstate, no change. When it's 0, we started with Gaussian beam, and we remain. In mixture, this is a coupling. This is still, I'm talking about this spin Z, and this is after the post-selection. Well, let me just say what we really did. We really did it, with, as I said, with polarization. How we do it with polarization, we have only 2 eigenvalues, 3 eigenvalues. So we made a trick. Spin 1 was H. Spin -1 was V. And spin 0 was no coupling. In coupling, this corresponds to spin 0. So no coupling. Of course, nothing happened to our beam because we did no coupling. Polarization, this is kind of the same birefringent experiment like the first one. And the second one, only with post-selection. We made birefringent and we put post-selection. And so we had these 3 cases. The original Gaussian beam without change, mixed beam, and this is this superposition. Now, the claim is that this superposition is much close to this than this one. How you compare them? The average is always 0, all 0. So how we can compare between 2 different beams? The way to compare between 2 different beams is to try to interfere. If the beam are the same, so we can get very good visibility in principle 1. So how much the best visibility we can get is a measure how close the beams are. And and in this way, there is a very simple connection. This Burroughs angle, it's really R cosinus to the maximal visibility we can get, maximal when we make best our effort to make it entangled as possible. And so in both cases work, both for mixed state and another case. We have to look on visibility, on the maximal visibility. So this is the experiment. The reference, we did nothing. So we still had Gaussian beam. Here we put our birefringent, which made a small splitting, and then we look on this visibility. We also, in another experiment, we put this our polarizer, so it was weak value because now pre and post selected. So again, it was still somewhat different. We look on the best visibility. And so we could compare between these 2 cases. This is theory, and this is our results. Again, this is theory. We tell us this is as a function of kind of a strength of the interaction. So it's supposed to get 0, the visibility when the interaction is 0, but we didn't get it because how tried we get, maximal visibility we got, it's 99, a little more than 99%. Still, there are some imperfection. But we could model this imperfection, and when we model the imperfection, we know how it will change, how it will change the visibility and how it will change this Burroughs angle. And this solid lines and dashed lines, these theoretical lines. as you see, theory and experiment kind of showed, at least we could see really the dependence in case of expectation value, because there was some big deviation. In case of weak value, we almost didn't see any deviation. We couldn't really see these things. One before the last slide. This is the first experiment. It was kind of really the second experiment. They were related. One can interpret what we did before as a robust measurement of the weak value of the polarization operator. Both experiments with polarization operator, and here we had pre and post selection every time. But what was special here, we had the same measuring device. Our photon was the same measuring device for polarization in every place here. If we consider post selection, this is really kind of a weak measurement of pre and post selected system. In our first experiment, the point was that this photon was going there with almost probability 1. Wasn't exactly probability 1, but conceptually was probability 1. But otherwise, it's really the same story.
They're all identical?
Yes. So this is summary. I will just leave it here. And thank you.